My name is Larry, and welcome to the newest installment of the Old Gazer channel, which is dedicated to helping beginning or inexperienced amateur astronomers work your way through the sometimes confusing, sometimes intimidating, but always interesting learning curve associated with this great hobby. So, if first time viewing, welcome. If you've viewed before, then welcome back. And with that, let's just get started. If you saw the last video, and by the way, if you haven't seen that, I think I might suggest that you might want to go back and watch that one before you view this one, because I'm doing a series of videos on telescopes. Last one was on Telescopes 101. This one is sort of Telescopes 101 Part 2, so it might be helpful to see what was discussed in the previous video before you watch this one, but probably not really necessary. We're going to continue to talk about telescopes in this video, and today we're going to talk about what might be called some metrics associated with telescopes, some numbers, if you will, some characteristics associated with telescopes, and we'll talk about what these things are and why they're important, especially with regard to helping you choose a telescope that might best fit your needs or what you want to do as an amateur astronomer. So let's just do that today. The first thing that I want to talk about is arguably perhaps the most important metric associated with a telescope, the most important characteristic of a telescope, and that would be the telescope's aperture, the aperture. Well, what do I mean by aperture? Aperture is simply the diameter of the objective lens or the primary mirror in a telescope. How wide, how far across that telescope lens or mirror is. Aperture is an indication of the amount of light that a telescope is able to gather. The bigger the aperture, the more light the telescope can gather, and therefore the more things you're going to be able to see, and the better you're going to be able to see them. Now let me see if I can sort of present something that might make this a little bit clearer and easier to understand. Let's consider for the moment the human eye. The pupil in a human eye has a diameter of about 7 millimeters, more or less. Now, if you're old like me, it's less than that, unfortunately, but typically the diameter of a human eye is about 7 millimeters. Now, our eyes are marvelous things. They can collect the light that we need to see, and just unbelievable how they work. But a 7 millimeter hole is not a very big hole to collect light. That's the hole that the light is coming through when it's coming into our eyes and enabling us to see things. Now, consider, for example, that this small if you would, just suspend belief here just for a moment and imagine that the apertures in these telescopes are pupils. So let's say that the pupil of this telescope, the aperture or the pupil of this telescope, which is the diameter of this objective mirror in the front, that diameter, that pupil is 70 millimeters in diameter, which is, of course, 10 times greater than the pupil of a human eye. So not surprisingly, this telescope is able to gather a lot more light than the pupil of our eye is able to gather. And therefore, we can see dimmer objects, we can see more things, and we can see them better through that telescope than with the unaided eye. This telescope has a mirror in the back, and the diameter of that mirror is 127 millimeters, which is 5 inches. And that's a lot more, of course, than either the eye or this telescope. So we would expect to see even brighter objects, see more things and see them better through this telescope than through that one because it has a larger aperture. And the same with this one. This telescope has an aperture of 203 millimeters, 8 inches. And of course, you can see a great deal more light. This telescope can gather much more light than this telescope, that telescope, and certainly the human eye. In fact, if I remember my specifications correctly, this telescope can gather over 800 times more light than the unaided human eye can gather. So, apertures enable us to see more things and to see them better. Because as they get bigger, that's more true, because the bigger the aperture, the more light the telescope can gather, and the more things you'll be able to see, and the better you'll be able to see them. Okay? You might infer from that, hey, I just want to get a telescope with a huge aperture. I want to see more things and I want to see them better. So let's just get a huge aperture. That's good thinking, and theoretically, that's the right way to look at it. But of course, there are some realistic, real-world constraints that kind of limit the amount of aperture that we can have in our telescopes, especially us amateurs who do backyard observing for the most part. The first of these, of course, is cost. You can imagine and understand that as the aperture of a telescope gets bigger and bigger and bigger, so also does the cost get bigger and bigger and bigger. And so there comes a point at which, it might pass beyond the realm of what we're able to afford. So, in a very real sense, for most of us in the real world, the size of aperture that we can get is a direct function of how much we can afford. There's a second significant constraint involved here also, and that has to do with the portability of the telescope. As apertures get bigger and bigger and bigger, the size of the telescope gets bigger and bigger and bigger. The weight of the telescope gets more and more. The unwieldiness of the telescope, the difficulty in handling it becomes greater. And so it doesn't do you any good to have a tremendous amount of aperture if you've got a telescope that you can't lift and move around when you need to move it. So you've got to keep the size of your telescope within the realm of some measurable, reasonable amount of portability. There's an axiom in amateur astronomy that says that a telescope that's so big that you can't move it around will be a telescope that's never used. It'll just sit in your garage or in whatever room of your house or apartment or whatever where you keep your telescope when it's not in use. It'll collect dust and it'll never be used, and you won't be participating in the hobby. So you can't get more telescope than you can reasonably expect to move around. So, what it comes down to is you have to find that sweet spot between aperture, cost, and portability. And when those three things come together in the right way, then that's the right telescope for you. Now, in my case, that sweet spot is manifested by this 8-inch Schmidt-Cassegrainian telescope right here. It's got an 8-inch aperture, which is a good aperture that gives you a lot of good things to look at in the night sky. This whole rig costs less than 50 pounds. The tripod, the mount, and the telescope, which, believe it or not, even at my age, I can somehow manage to handle that. But even when I can, if I want to be more careful, or this can be disassembled into 3 major parts, none of which weighs more than 15 or 20 pounds, and you can disassemble it, take it out, reassemble it very quickly, very little time, and handle that without any problem. And, price-wise, it took a while before I could get to this point, but I bought this telescope at retail right out of the box for $1,200. Now, it is a computerized telescope, and so a lot of the cost is caught up in the sophisticated, fairly sophisticated mount of this telescope. But I finally got to a point where I could manage that. And so this telescope, for me personally, happens to hit that sweet spot pretty well. It's a good combination or meeting of aperture, portability, and cost. And that's why this is a good telescope for me. You'll have to make your own choices and come to your own determinations over time to find out which telescope best hits your sweet spot. And that'll be the one that you'll use the most and that you will enjoy the most. So anyway, that's aperture. The bigger, the better. But of course, you can't get but so big before other concerns start to place realistic limitations on the size of the telescope that you could probably have. Let me just mention before we leave the subject of aperture that it is not the size of the aperture of the telescope that determines how much an object is magnified in the telescope. That's a common misconception among beginning astronomers or people who know little or nothing about telescopes or astronomy. The purpose of aperture is to gather light, and the bigger the aperture, the more light you can gather, and the brighter and better the object will be, the more detail you'll be able to see. So a bigger aperture gathers more light and presents you with a better looking object with more detail. It does not actually magnify the object. The magnification is done by the eyepiece, which we'll talk about a little bit in a minute, but not too much, because we're going to have an entire video later on about eyepieces. But the aperture does not magnify the object. It simply gathers light so that you can see the object better and see the detail associated with the object better. Okay? Let's move on to another metric here, which is called focal length. Now, if you saw the previous video, well, you know we touched on focal length a little bit. Let's get into it a little bit deeper here. What is focal length? Focal length is defined as the distance from the point at which light first hits the optics of your telescope until it gets to the end of the light path and brings the object that you're looking at into focus. Light enters the telescope. It's either refracted or bent, or reflected, or both, in such a way that it passes through the telescope and eventually comes to a point where all of the light rays, if you will, that's a simplified way of describing it, but where they all come together at a point and you have a focused image that you can actually view or look at. That is focal length. This telescope, for example, the light hits the primary, the objective lens right here, passes all the way to near the back there where it comes to a point of focus. So the distance between here and there is the focal length. And in the case of this small refracting telescope, that focal length is 350 millimeters. In this telescope, the focal length begins at the primary mirror and comes all the way forward to where the light is passed out through the side of the telescope. The focal length of that telescope is 1,000 millimeters. And the focal length of this one here is 2,032 millimeters. Now, you may wonder, how can you get that much focal length in a telescope tube that's only about 1.5 feet long? How can you get 80 inches of focal length in an 18-inch tube? Well, we discussed how that's possible in the last video, but just to review it briefly here, when light enters this telescope, it hits this lens in the front, it passes to a primary mirror in the back, it's reflected off of that to a secondary mirror in the front, and reflected from that back to the primary mirror again, where it passes through an opening to be focused. So in effect, the light has passed through this telescope 1, 2, 3 times. And that total length is what determines the focal length of the telescope. So that gives these so-called Schmidt-Cassegrainian telescopes a big advantage, because you can get a lot of focal length in a relatively compact tube, which eases portability a great deal. So at any rate, that's what focal length is. Now, why is focal length important, and how does it impact, what you can see and how you can see it? Well, the longer the focal length of a telescope, the more potential magnification there is. Now, let me illustrate this by just doing a few, simple calculations here. The magnification that you see when you look through a telescope, the number of times that object has been magnified, is determined by an equation that's equal to the focal length of the telescope divided by the focal length of whatever eyepiece you happen to be using. Now, eyepieces have a focal length just like telescopes do. So the way you determine magnification is you divide the focal length of the telescope by the focal length of the eyepiece you're using. Let's assume that we're using an eyepiece of 10 millimeters. Let's calculate the magnification that would represent when used in each of these 3 telescopes, which have different focal lengths. This one has a focal length of 350 millimeters. So if you divide that by 10, you get 35. If you use that 10 millimeter eyepiece in this telescope, you're going to get a magnification of 35. 35x is how that's usually expressed. This telescope, which has a focal length of 1,000 millimeters, is going to give you a magnification of 1,000 divided by 10, or 100. So you're going to get a magnification of 100x using this eyepiece in this telescope. And this telescope, let's round that off to 2,000 millimeters as the focal length, just for ease of calculation. If you look through this telescope, through this eyepiece, using this telescope, 2,000 divided by 10, of course, is going to give you a magnification of 200x. So we've used the exact same eyepiece in all 3 of these telescopes, but the determining factor in the magnification that we've gotten, as you have no doubt understood by now, is the focal length of the telescope. So the focal length of a telescope gives you the potential factors into the potential magnification through that telescope. The bigger the focal length with a given eyepiece, the higher the magnification. So if you want higher magnification, you would want to use this telescope because it gives you the most potential for high magnification with a given eyepiece. If you want lower magnification, such as if you're looking at a deep sky object, then you would use a telescope like this and you would get a much less magnification. So that's just something to keep in mind as you think through getting to that point of decision in buying your first telescope. Do you want one with a long focal length or one with a short focal length or something in between? And that helps you to understand that if you're looking for high magnification, you'll want a long focal length. If you're wanting lower magnification and a wider field of view, you'll use a telescope with a shorter focal length. Which brings us into the discussion of the next metric we want to talk about here, which is the focal ratio of the telescope. That's different from focal length now. We're talking about the F ratio or the focal ratio of your telescope. Well, what is that? You might be able to relate better to this if you think about digital cameras, DSLR cameras or old style 35 millimeter cameras that have an adjustable lens or adjustable controls on it so that you can control the size of the opening in the camera. If you're familiar with that, you know that an F number or an F stop of f3.5 is going to give you a pretty big opening in the camera aperture when you press the shutter. And of course, that bigger opening is going to allow more light to come through. If you, however, set your camera at an f stop or an f ratio of 16, the camera is going to open up just a little bit, and that's going to allow much less light to come through that opening when you take a picture. That's the way it is with an f number or an f ratio of a telescope. By the way, here's how you calculate the f ratio of a telescope. The f ratio is equal to the focal length of the telescope divided by the size of the aperture of the telescope. So 350 millimeter focal length with this telescope divided by an aperture of 70 gives you a focal length of 5. Not a focal length, pardon me. It's easy to get those confused. A focal ratio, an F ratio of 5. This is an F5 telescope. This telescope, which has a 1,000 millimeter focal length, has an F ratio of about F8. And this big telescope, with its 2,032 millimeter focal length, has a focal ratio or an F number of F10. Now, what's the significance of all of that? What's the difference between an F5 telescope and, say, an F10 telescope? Well, it's pretty significant, really, especially with regard to taking photographs of objects in the night sky. A telescope with a large F ratio, like this F10 scope, is sometimes referred to as a slow telescope. And that means it is able to capture or accumulate less light per unit of time than a telescope with a faster focal ratio. So you can imagine taking time exposure photographs, long exposure photographs of objects in the night sky. You'll be able to collect a lot more light faster by using a telescope with an F ratio of 5 than with a telescope with an F ratio of 10. And that's why smaller telescopes with wider fields of views, faster telescopes are normally better for most forms of astrophotography than so-called slower telescopes. This would be a fast telescope at f5, a slow telescope at f10, and that's basically the implication of those F numbers. Now, you can, in some instances, in fact in many instances, you can buy a device known as a focal reducer, which will lower the F ratio number of a telescope. For example, this F10 telescope here has an optional focal reducer that you can buy for it. It costs about $160, I believe. And when you mount that on your telescope, it effectively changes this from an F10 telescope to an f6.3 telescope, which has a wider field of view, a flatter field, and a lot more light gathering capability per unit of time, which then greatly enhances the capability of this telescope to do astrophotography, because now you can collect more light per unit of time when you're taking long exposures, and you'll get a wider field of view. So you can modify telescopes in that way by using a focal reducer. But that's the implication of the F ratio. Now, maybe you've been able to put it together already without me having to say it. You can probably take it from this point. The kind of telescope that you want to get will depend in very great measure of what you want to do exactly with that telescope. Are you going to want a telescope with a shorter focal length, a wider field of view, and a faster telescope that can collect more light per unit of time? Or do you want a telescope with a longer focal length, much greater magnification potential? Which kind of telescope do you need, and when would you want those? Well, it's very simple, really. If you're viewing or photographing the moon or the planets, this telescope would be best. It has a long focal length, gives you a pretty narrow field of view. It allows for very high magnification. You can get a lot higher magnification with a given eyepiece in this telescope than you can in these other two. And that's what you want if you're viewing the planets, or if you're looking at the detail of craters or formations on the moon, for example. Those things are going to be small in your field of view. You'll want a narrow field of view to bring that in a little bit, and then you'll want as much magnification as you can get to bring out as much detail of that planet or of the surface of the moon as you can get. Now, of course, remember in a previous video we talked about how seeing conditions affect how much useful magnification you'll be able to use. But assuming good seeing conditions, you can get very high magnification out of a scope like this when you're viewing or photographing the moon or the planets. It's not good, however, for viewing deep sky objects. In viewing deep sky objects, you need a broader field of view. And that's because many deep sky objects are actually very big. Yeah, we don't realize that because we can't really see much of them. But the Andromeda galaxy, for example, has an angular size that is 6 times greater than that of the full moon. And so it takes a lot of field of view to get the entire Andromeda galaxy within the field of view. And so you would not want a long focal length and a narrow field of view. You would want a short focal length and a wide field of view. And if you're taking pictures of those deep sky objects, you'll want a faster telescope so you can take long exposures and gather more light faster in doing those exposures. So it depends on what you want to do. If you want to do primarily, if you're interested primarily in the moon and the planets, this would be a much better choice. If you're interested primarily in viewing and photographing deep space objects, then this little telescope, surprisingly, would be a better choice because it gives you wide field of view and faster, better capability of accumulating light during long exposures. What if you are equally interested in everything? Suppose you're equally interested in the moon, the planets, and the deep sky objects. You want to see it all. You want to have your cake and eat it too. You're just interested in the whole gamut of astronomical objects. Your approach then would be to buy 2 telescopes. You could buy one like this for the moon and the planets, and something like that for the deep sky objects. Or you could make some modifications to one of these telescopes to make it better for viewing all kinds of objects in the night sky. We've already discussed this. I don't want to belabor the point, but this telescope works very well for me. I'm interested in all the objects in the night sky, the moon, the planets, and deep sky objects. And this telescope gives me the best all-around capability to view and image all of those things, but only by use of the focal reducer that we've already discussed, which is attached to the back of the telescope. I essentially can have 2 telescopes in one with this one. I can take that focal reducer off and have a very good telescope for viewing the moon and the planets. I can put that focal reducer on, That was almost a really good slip up there, wasn't it? Anyway, I can put that focal reducer on here, and it becomes a reasonably good instrument for viewing deep sky objects, because it's suddenly got a shorter, a smaller F ratio, can gather more light per unit of time, and it has a wider field of view, and it serves to flatten that field of view so that everything looks good throughout the field of view. So that's my answer to this issue of how do you get something to view everything that you might want to see. Again, if you're only interested primarily in the moon and the planets, just one telescope with a long focal length is good. If you're only interested primarily in nebula and galaxies and star clusters and deep sky objects in general, then a smaller telescope with a shorter focal length, a wider field of view, and a faster telescope that can collect light better would be the choice there. Since I like all of that, rather than get two telescopes, I just choose to use this one and modify it with that focal reducer at those times when I want to view or image deep sky objects. Okay? So that's kind of what I wanted to get at with this video. I'm hopefully leading you in the direction of trying to help you to decide what kinds of things you want to take into account to get a telescope that will best meet your needs. Now, just because I like this by the way, this probably would be a good time to say right here that I receive no form of compensation or recognition of any kind whatsoever from any manufacturer, retailer, or anybody that has anything to do with the telescope industry for mentioning or promoting or recommending any of their specific products. The things that you hear on these videos are strictly my own thoughts, my own opinions, my own views. I'll be positive when I feel that way. When I don't like something about a telescope or a piece of equipment, I'll be quick to say so. So just wanted to get that out of the way so you'll know where I'm coming from here. This telescope works very well for me. This is probably the last telescope I'm ever going to buy. I use this far more than these other telescopes combined. And it's just, works well for me. It's that sweet spot for me between aperture, portability, and cost. And I can get a good all-purpose telescope in one by the use of the optional focal reducer. So that's just me. You may decide something different. You might like another telescope. You might come to your own conclusions. That's what you need to do. You just need to use the information that hopefully you're gaining about telescopes to come to that point where you can make a good informed decision about what you want to get for your first, quote, serious telescope. So I hope that was all helpful. I hope that was understandable. Again, I'm sort of a simple-minded guy. Sometimes I might not be able to explain things well. Probably I've oversimplified some things in this discussion today. But maybe you get the gist of what I was trying to say here today about some of the major important metrics associated with telescopes. And maybe you can put this information together with what we discussed in the last video, where we just talked about in high-level terms what telescopes are and what their components are and how they function and that kind of thing. So maybe this will put you on the road to determining what you might be looking for in a telescope, which has to be your decision, not mine. I'm just trying to give you some information. I probably shouldn't have told you how much I like this telescope, but if you're a beginner, an inexperienced amateur astronomer, you're really not ready for this telescope yet anyway, and I will not be recommending that you get this telescope as your first series telescope, which you will learn in the next video. So next time I'm going to make some specific recommendations for you as to possible good choices for a beginner's telescope, a good quality beginner's telescope that you can use to help you pass through the learning curve of this magnificent hobby that we call amateur astronomy. So we'll go there next time. Let's call it quits for now and wrap this one up. Let me just say that if you have enjoyed or benefited from this video, and if you enjoy this channel and would like to see more videos in this channel and to be informed when new videos are available, perhaps you would do me the service of liking this video and maybe even subscribing to the channel. And if you should elect to do so, I would appreciate that very much. So that said, let's close for now. As always, let me just thank you so very much for taking the time to tune in. And until next time, let me wish you clear skies and good viewing.
Subscribe.